Now, dear friends, let me discuss few concepts from dynamic stability in tutorial 4. What was dynamic stability? For static stability, we realize that it is only the initial tendency that matters. If it has an initial tendency to come back to equilibrium, we say statically stable. But for dynamic stability, not only initial condition, but in a finite time, it should come back to the equilibrium. Right? So that is, if I try to see like this, suppose I have disturbed a system and it tries to come back to the equilibrium and this. So we are now talking about dynamic stability. We are now introducing the concept of transient. How is response? Is it coming back to the equilibrium or it is diverging? It's possible it has the initial tendency to come back to this, but every time this is further going up and up like this. So you could see it has got initial tendency as soon as it crosses the equilibrium. Say it is equilibrium, it goes, again it tries to come back to equilibrium, again overshoots, and the amplitude goes on increasing. So this is a typical case of dynamic instability, and typically this is phenomena close to resonance, right? Okay. Now for aircraft, how we postulated mathematical model to study dynamic stability? We said first we will develop equations of motion. So we started with equations of motion, and the moment we talk about equations of motion, we realize that we have to fix axis system. And we said, okay, this is the x, this is the y, and this is the z, which is a body fixed axis system. That means as a body rotates or moves, axis also moves along with the body. We wanted to develop equations of motion, and you know that to develop equations of motion, we need to use Newton's laws of motion, where F is equal to ma. Force is the cause, the effect is acceleration, and this acceleration is inversely proportional to the mass property or inertia for a given force, which you all know. But what is the condition? Condition is this relationship is valid in inertial frame. But see, we have chosen an axis in the body fixed norms, that is, the axis is fixed to the body, so as body rotates, axis rotates. So definitely this axis is not an inertial frame. So how to apply F equal to ma? So we said, okay, we will use earth fixed axis system for our dynamic stability analysis as an inertial frame. What was the logic behind it? Although we know earth is rotating, it is a non-inertial frame. However, for dynamic stability analysis, the duration is so short, maybe a few seconds, and we can assume during that time the acceleration or the rotation of the earth is negligible. And for all approximation, we can assume this to be inertial frame for our purpose of dynamic stability analysis. Okay. Now the question was, if I am trying to write the equations of motion in inertial frame, that means what will happen? So we know that F is d by dt, rate of change of momentum, and you know this is nothing but m dv by dt plus v dm by dt. So another approximation we make. We said that we will neglect this second term, and as if we will assume that dm by dt is 0. But you know, the aircraft has fuel and there is a huge fuel consumption. And what is the logic again given here? We said, since we are doing dynamic stability analysis, it is for a few seconds of response will be utilized for analyzing the dynamic stability of an airplane. So for the small second, we'll assume that the fuel has not changed, or the mass of the whole airplane has not changed. So we said F equal to m dv by dt. But we know this has to be in inertial frame. Okay? But we are working in fixed frame, body fixed frame. Suppose we work in inertial frame, one of the issues will be when I talk about rotation. See, if I use the moment equation, the moment will be rate of change of angular momentum. And the angular momentum vector will have moment of inertia as inertia properties. So what will happen? If I work in inertial frame, as the body rotates, so the moment of inertia about the inertial frame will go on changing. So that will complicate our analysis, right? Second thing we realize that the aerodynamic forces, they depend upon the relative airspeed. So from that angle, the body fixed frame will be very, very important. So speed of the aircraft with respect to the atmosphere, relative to wind, relative to atmosphere will be very, very useful, because after aerodynamic forces depend upon relative air velocity. So we had a motivation to work in body frame for these two reasons. But how to do that? We need to work in inertial frame, but we have a motivation to work in body fixed frame. So what is the trick? We said, after all, dv by dt is the vector differentiation. So we use this relationship dA by dt in inertial frame is dA by dt in body frame plus omega cross A. Right? So this relationship helps us to work in body frame. What is the message? That either you work in inertial frame, or if you want to work in body frame, which is our motivation, you can work provided you give this correction, omega cross A. Right? And that is how the equation of motion were developed. This is a subtle understanding you must have. Okay? Now whenever we applied this, we found the equation of motion in terms of V dot, W dot, P dot, Q dot, R dot, etc. Right? What we did? We used small perturbation theory. And what was the understanding of small perturbation theory? That the perturbations are small, so that we can write total u is u1 at steady state plus perturbed velocity u. So we are assuming that the changes are such that linearity is maintained. Similarly, we write v equal to v1 plus v, w equal to w1 plus w, p equal to p1 plus small p, like this. Then you use this in the equation, and after modifying with the assumption that product of two perturbed quantities are almost zero, they can be neglected, then we found out equations of motion, which we refer to as longitudinal perturbed equations of motion. Okay? So in that, if you remember, when we developed longitudinal perturbed equations of motion, what was longitudinal? Longitudinal means the motion is either this u or along z, w, and the pitching motion. These three only. And we assume that this is a result of a small perturbation. So this is not going to influence lateral motion or a directional motion. Right? In that, if we check your notes, we have some term called Fx. And what was Fx? Fx was termed as perturbed aerodynamic force. Right? And when you say perturbed aerodynamic force, we need to estimate this perturbed aerodynamic force, and we wrote Fx equal to Fax, the function of, we wrote u by u1 alpha q delta E, etc. For Fx, we said q effect is negligible, and we wrote this Fx as dFax by du by u1 into u by u1 plus dFax by d alpha into alpha plus dFax by d delta E into delta E, like this. What was the understanding of dFax by du by u1? All these derivatives said this to be evaluated at steady state. That is important. Okay, and we derived some expression for this. Those you could see that. And this dFax by du by u1, these are termed as stability derivatives. But these are dimensional. That's the catch point. Dimensional. Dimensional stability, because they have dimensions. Okay? This one we did. Then what we realized, once we develop the equations of motion, which are called longitudinal perturbed equations of motion, we took Laplace transform, right? And through Laplace transform, we developed equations of the form A is 4 plus bs cube plus cs square plus ds plus E equal to 0, right? And numerically, you can find the solution for this equation, and you realize that for most of the airplane, when I solve this equation for longitudinal perturbed equations of motion, we get roots, let's say lambda 1, lambda 2, as typically, let's say, I give number 1.0 plus let's say 2.5 j, lambda 3, 4, let's say minus 0.08 plus minus 0.5 j. Important thing is to understand you get two pairs of complex conjugate. That means this root tells you that the response, which I will use to characterize this transient, I find they are oscillatory in nature. Okay? One thing, they are oscillatory in nature. Also, we realize one thing, that if I closely see this root, the real part of one complex conjugate pair is large negative as compared to the other pair. You could see from here. So immediately I know, although both are oscillatory, this will decay faster than this. Okay? Because the real part decides the decay. E to the power zeta omega n t type, you know. If that is true, then if I try to understand and give physics to the actual airplane, we have see that typically airplane, when they are disturbed longitudinally, then two distinct types of modes are generated. One is called short period mode, another is called phugoid mode. Okay. What is the short period mode? Short period mode will correspond to this because its real term is large negative. And typically, if you see the airplane is moving like this, cruise, if I give a short elevator input, one mode will be like this. It will immediately come back to the equilibrium. This is transient. So that is the short period mode. Phugoid mode is, if I let's say excite is phugoid mode, maybe I hold the elevator for long, you'll find the airplane will come back to equilibrium, but it will go on doing like this. Then it will come. So long period mode. So that is the phugoid mode. And we have done some approximation to find out their natural frequencies and their damping ratios. Right? And we have indeed seen that damping ratio zeta for short period is large compared to zeta for phugoid mode, where phugoid mode is weakly damped mode. Right? So this should be very, very clear, and you should also know, if I want to find out the omega n for any complex pair, and the best way to do it is to write the equation of motion s square minus sum of the roots into s plus product of the root equal to 0, and you can use those roots, and from there you get an equation in terms of s square plus, let's say, a s plus b equal to 0, and then compare this with s square plus 2 zeta omega ns plus omega ns square equal to 0, typically second order system, and you can find out through comparison what is the value of omega n and value of zeta. What is the understanding? That the overall longitudinal dynamics for most of the airplane can be resolved into two second order systems. One is here short period, one is phugoid. And once you know this, I can easily find out what are the natural frequencies, what is the damping ratio. We also use this understanding and try to approximate the matrix and got expression for short period and phugoid mode. Okay. We have also talked about SAS, which is stability augmentation system. What was that? The understanding is this. Suppose airplane is having a zeta equal to 0.2, but you want zeta to be 0.6. One way to change zeta is change the tail volume ratio, because the zeta largely depend upon CMQ, and you know CMQ has VH, tail volume ratio, as one of the parameters, variables. So if I want to increase zeta, I have to increase the tail volume ratio. But suppose you don't have that option to increase the tail volume ratio, you want to change zeta online. So what was the concept? Concept was SAS. And the understanding is like this. This is the aircraft. And let's, this is here, you write Q. I tap Q. This is K. What I do, I deflect elevator proportional to this Q. I deflect elevator proportional to this Q. Then what will happen? As I deflect elevator, so what is delta Cm? I am getting, because of elevator deflection, that is Cm delta E into delta E, which will be equal to Cm delta E into KQ, right? And CMQ is defined as delta Cm by Q C bar by 2V. So I write this as Cm delta E into delta E, which is delta is nothing but KQ divided by Q C bar by 2V. So QQ gets cancelled. So this becomes 2V by C bar into Cm delta E into K. Okay. So now you could see that let's see for zeta equal to 0.2 CMQ, I can calculate it was, let's say, minus 10.0. Let's say some number. To make zeta 0.6, CMQ required is minus 20, let us say. So what is the procedure? Procedure is that this is typically delta CMQ. So CMQ is minus 20. So CMQ new minus CMQ old. This is nothing but minus 20 minus minus 10. This should be equal to 2V by C Cm delta into K. Cm delta is fixed, velocity is fixed, C is fixed. So you have to alter the value of K. So you can go on changing the value of K and get the desired online value of CMQ required to ensure zeta is 0.6. Right? So you could see how beautifully you can use SAS to change the damping ratio. Similar thing if you want to do for natural frequency. If you want to change natural frequency, what you have to do? This is the aircraft. This is alpha. You tap alpha and say K, and this is again delta here is K alpha. Okay, that goes to the plant. So what happens? I write delta Cm equal to Cm delta E into K alpha. Okay? Because it's nothing but Cm delta E into delta E, and delta E is K alpha. So Cm alpha, which is nothing but delta Cm alpha, will be Cm delta E into K. And you know, if you want to change natural frequency omega n is goes with minus m alpha, and m alpha is nothing but half rho v square sc bar Cm alpha by Iyy. So if you want to change omega n, one way to change Cm alpha, and to change Cm alpha, you know, Cm delta into K. So electronically you change the K value and get the desired Cm alpha to get required m alpha to have desired omega n. So that is also another way of utilizing SAS for a specific purpose. But all these things are fine, but do not forget that the moment I am using delta E equal to K alpha, please understand, if you see the CL equation, that is CL naught plus CL alpha into alpha plus CL delta E into delta E. So and delta E equal to K alpha, so your CL also gets modified. Now CL becomes CL naught plus CL alpha into alpha plus CL delta E into K alpha. So your CL also gets modified because of this additional term. So you have to be careful that you have to make a total optimized algorithm to see that the final requirements are not disturbed much. Okay? So I thought I will go for a revision on this. I have requested one of my friend, Dr. Dipu Philip, to give you one lecture where he will be talking about different types of aircraft. Okay? And you should know that. You should see, listen to that lecture and get an idea about why all these theories, what have we achieved. And if you see the evaluation of aircraft, please understand this evaluation was not possible unless our basic understanding was clear. Okay? Thank you very much.